loop equations. So I'll be using the same circuit. So the values of the parameters are given. VCC is given as 16 volts. Collector resistance 3 kilo ohms. R1 is 56 kilo ohms. R2 is 20 kilo ohms. RE is 2 kilo ohms. And alpha is given. So determine the coordinates of the operating point. So we need to calculate the values, that is the coordinates. So the coordinates will be the collector current and the collector to emitter voltage. So if you see the DC load line, the two connecting points will be the collector current and the collector to emitter voltage. So we are supposed to calculate IC and VCE for this particular circuit. Given common emitter CE germanium transistor. So if it is particularly given for germanium, you have to take accordingly the base emitter voltage. The VBE value will change for the material that is used for the BJT. For silica, we can take it as 0.6 or 0.7. For germanium, we have to take it as 0.3. VBE as 0.3 volt. Okay, by default, VBE for germanium is 0.3 volt. Okay, and also alpha value is given. For common emitter, we need to calculate the current gain, which is beta. So we know this relation between alpha and beta. Okay, so using the alpha value, first we have to calculate beta value. So in some specifications, the HFV or the beta value, if it is directly given, you need not use this conversion. You can directly calculate, you can directly use the beta inside the calculation. Otherwise, from the given value of alpha, you can calculate beta, the current gain. Now, using the loop equation that is at the base. So using the potential divider arrangement, first of all, we will calculate what is the Thevenin voltage or the voltage VT that is calculated across R2. That is the voltage VT. So this VT will be the applied voltage VCC into the parallel resistance R2 divided by sum of R1 and R2. So we are writing the equation for VT first. So using this equation, first we can calculate VT. So now after knowing VT, then we can use this VT loop equation, and then we can find what is the collector current. Okay, so beta value is given, and VB is known, RE is known, RB is known, and let us find RB also. So RB will be the Thevenin resistance. That is Thevenin resistance RB will be the parallel combination of R1 and R2. So it is R1 R2 by R1 plus R2. So first you calculate what is the Thevenin voltage, that is VT, that is across R2. First you substitute for R1 R2 and VCC 16 volts. Calculate VT 4.21 volts. Getting this value. Okay, so now you can calculate a base resistance or the Thevenin resistance, which is parallel combination of R1 and R2. Okay, so now we have found the base resistance and the Thevenin voltage or the voltage at the resistor R2. Now let us use these and find inside the loop equation and find the collector current. Okay, now we are writing the loop equation around the base. So this VT can be written as this IB into RB, that is the parallel combination of R1 R2 base resistance plus the base emitter voltage plus the current that is flowing IE across RE. So this IE can be written as IB plus IC. So we are writing the equation for VT as IBRB plus VBE plus the emitter current into the emitter resistance. Okay. So now the base current is not given in the specification. So you can use the base current, that is collector current is given. Collector current is given. So we are supposed to use the beta, that is beta we have calculated using alpha, right? So beta is 66, which is known. So we can rewrite this IB in terms of beta. So we know that the current gain beta will be equal to IC by IB for common emitter configuration. So we are writing IB in terms of IC by beta. So we are rewriting this entire equation, everything in terms of IC, because IC is the unknown parameter we are going to calculate, right? So other parameters are already given in the specification. RB is given, VB is known, and beta is known, RE is known. Now let us substitute for all the parameters and calculate IC value. So VT is also known. So substitute everything and find IC. So just a simple substitution and arrange the parameters and calculate IC value. Next, we are going to use the loop equation on the collector side, and we are going to find VCE value. Okay, and so we can calculate IE value through IC. So generally, the emitter current can be written as base current plus the collector current. So we can approximate the emitter current equal to the collector current because the order of base current will be very less, very small. So we can directly equate collector current equal to the emitter current in most of the approximations for common emitter amplifier. Okay, and so writing the loop equation for the output side. So we already know that that is I think this equation I've already given you for the collector emitter circuit KVL. It is VCC, supply voltage minus the drop across the collector resistance, and minus drop, that is, so we can write VCC as sum of the drops of RC and collector to emitter plus the emitter resistance, drop across the emitter resistance, or that equation can be rewritten as VCE equal to VCC minus ICRC minus IE into RE. So the same equation we are using here to find VCE. Okay. Now you can substitute for IC, IE, RC is known, RE is known, VCC is known. So now you can directly find VCE. Okay. So now these are the operating points, that is IC and VCE. These are the 2 points where which will form the DC load line. Okay.